Math 1314, Tyler Junior College, section 3.4, zeros of polynomial functions. Other properties of zeros of f of x. The last two videos went a lot longer than I expected, so we'll make this one kind of short. There are two other things we can say about zeros before we get to the last topic. Number one is called the fundamental theorem of algebra, which sounds pretty simple and is a little tricky to prove, but not impossible. Fundamental theorem of algebra says that f of x is a polynomial function of degree n greater than or equal to 1. So the highest power is at least 1. Then f of x has at least one complex zero. So it could be real or it could be complex and have an imaginary part. Now there's a corollary to this, which is it's almost like a consequence of this, which I won't prove, we'll just state without proof. Up to multiplicity, your function has n zeros, not necessarily distinct. We just saw an example of that in the previous video. In the previous video, we had a function that started with x to the 4th power. That was its degree. And the zeros we got were 2, 2, negative 2 plus I squared to 2, and negative 2 minus I squared to 2. So this did have at least one complex zero. Any of these would suffice. And even though one of the zeros was repeated twice, if we counted according to its multiplicity, there were 4 zeros, 1, 2, 3, 4. So that's all this is saying. It's basically a cap on how many zeros you can get to a function. So if you're a 4th degree, you should expect 4 zeros. If you're a 3rd degree, you should expect 3 zeros. That kind of makes sense if you think about it, because if you were to factor something that started with a 4th power, factoring basically disassembles x's that got glued together. So we can only have up to 4 x's and 4 factors, and therefore only have up to 4 zeros. That's not the proof. That's a little too loosey-goosey to be called a proof. Second property of zeros. If your function has real coefficients, because there are polynomial functions, well, technically speaking, a polynomial function can have non-real coefficients. We just don't study them in this class, but they could have non-real coefficients. However, if a polynomial function has real coefficients, so there are no i's in the function, then non-real zeros occur in conjugate pairs. So for example, if x equals, well, we just saw one. I just erased it. Negative 2 plus I squared to 2 and negative 2 minus I squared to 2. Recall that conjugate pairs are complex numbers that aren't real, so they got an I part. But the only difference is the sign of the imaginary part is different. In this case, the imaginary part is positive I squared to 2, where in this one, the imaginary part is negative I squared to 2. In general, conjugates are of the form a plus bi and a minus pi. Of course, the a could be negative. So for example, if x equals 3 plus 4i is a 0 of f of x, and we're assuming it's a polynomial function with real coefficients, then x equals 3 minus 4i is also a 0. And the reason's actually pretty simple to explain. This doesn't constitute a proof. Answers like this come from doing the quadratic formula when you get a negative under the square root. But the quadratic formula has a plus minus parked in front of the square root. So if the discriminant is negative, not only do we get an imaginary answer, we get one with the plus in front and one with the minus in front. You could even go further to say that if you have an irrational number of a certain form, there's a conjugate. So for example, if 3 plus the square root of 2 was a 0 of a polynomial, now we have to say integer coefficients, then so would 3 minus the square root of 2. But that's usually not mentioned, so we're not going to worry about that. All right, so just a couple of comments about the nature of zeros of polynomial functions. The highest power, the degree, can tell us the most we can have, and if we count multiplicity, that's exactly how many we have. And non-real zeros of real coefficient polynomial functions occur in conjugate pairs. Can't have one without the other. We're going to need that in the last topic. See, short video.